What's up, folks? How we doing? Just trying to hone some chill vibes here. Getting ready to do this chapter 4, the rest of it. You guys did your exam. Good stuff. We're ready to move on, folks. Okay, let's turn that down, Bob. Oh, Bob, I love you. Okay, folks, hopefully you have watched the first video I recorded on chapter 4. What was that, number 11? I've lost track of the numbers. And hopefully you also watched that short demo video that I shared for you. So normally that's a demo that I would do live in the lecture hall. I love that electrolyte demo. But it is what it is. So watch that video. I think it's really cool. And it really is showing you why we call something an electrolyte, right? Hopefully you gathered from that demo that when an electrolyte dissolves in solution, it can conduct electricity because there's a separation of charges, okay? So now we're going to really get into this, like discussing the difference between strong electrolytes and weak electrolytes, okay? So a strong electrolyte, there's several examples. Soluble salts, strong acids, strong bases. We're going to talk about what this whole soluble thing means as we progress, okay? A weak electrolyte is a substance that partially ionizes when dissolves. Okay, so what does that mean? Well, I'll give you an example. So HCl is a strong acid. Okay? Strong acid. And by saying strong acid, no, this isn't the stuff you take at Burning Man. There is a chemical definition of strong acid, okay? And that definition is that it completely ionizes when dissolved. So that means now this HCl aqueous, okay, when it dissolves in a solution, it completely breaks up into H plus and Cl minus, okay? So for example, suppose if I had 1.0 molar HCl, okay, then and it's aqueous, then what that means is I would have 1.0 molar of H plus ions and I would have 1.0 molar of Cl minus ions. So it's completely ionized. 100% of the molecule is ionized, okay, broken apart. What about something like acetic acid? So I'll write that down, HC3C. I'm going to write it down, sorry, a little different. CH3COOH aqueous, okay? And this acetic acid is considered a weak acid, which makes it a weak electrolyte, okay? And when acetic acid dissolves in water, it actually undergoes something that we call equilibrium. So it has these arrows here, okay? So let's see, the best way I can draw these arrows, let me do that again, okay? So I'm going to draw the forward arrow being really short and the backward arrow being really long. And we're gonna talk about equilibrium in Chem 110. The next semester, that'll be a big subject of this class, okay? So we'll discuss what that means in more detail in Chem 110, but what it means for us for now, that if I go and dissolve some acetic acid into solution, not all of it will dissolve. That's what this kind of arrow is representing. So only a very small amount of it goes in this forward direction, okay? And so that means the majority of it, this backward arrow is showing you that the majority of it remains unionized, okay? It can be dissolved, right? It can be a homogeneous solution, but when it's dissolved, the majority of it will not be broken apart into its respective ions. So for example, if I had 1 molar acetic acid and I then ionized it, I actually even have to add like several significant digits here to show the effect. Okay, so if I call this 1.000 molar, okay, once I dissolve this, okay, as it turns out, I would only have about 0.003 molar acetate and about 0.003 molar H plus, all right? Which means now, considering this, I would actually then have about 0.997 molar acetic acid remaining in the solution. And for my HCl, back to the strong acid case, this would mean that I would have 0 HCl bonded together. None of it would be bonded together. It would all have been dissociated, okay? Whereas the acetic acid, 1 molar of that would transform to about 0.997 molar would remain associated, bonded, and the very small fraction of that would remain unbonded, okay? So it still ionizes, but only partially. And this is the story, folks, between strong electrolytes and weak electrolytes. And we're going to see this manifest not only in strong acids, strong bases, weak acids, weak bases, but also in what we call soluble salts or insoluble or slightly soluble salts, okay? And so this picture, right, this kind of summarizes that demo. And the idea of this thing is that when you had a strong electrolyte, the light bulb lights up a lot more because there's a lot more ions to conduct that current. However, when you have something like acetic acid, the light bulb still lights up, but not as much, okay? And the picture doesn't do a great job showing that. So hopefully that demo really hits home, okay? So let's keep talking about acids and bases. So for the rest of just this lecture, I'm going to focus on acids and bases, okay? So there are several definitions for acids and bases. The first one we're going to focus on in this class is the Bronsted-Lowry definition, and that is an acid is a proton donor, a base is a proton acceptor. I want you to commit this to memory. An acid is a proton donor, a base is a proton acceptor. And when we're talking about a proton, specifically, we are talking about the H plus ion, right? If you recall, hydrogen as an atom, right, has 1 proton and 0 neutrons and 1 electron, okay? So now when you go and ionize this thing, when you remove an electron from it, literally the only thing you have, I wrote that backwards, literally the only thing you have is a proton, okay? That is acid. Acid is a proton. That's what's doing the corrosive acidic reactions we normally associate with acids, okay? So let's look at this reaction. Hydrochloric acid, HCl, a hydrogen bonded to a chlorine. Okay, that is the proton donor, so that is the acid. And now in this case, in this reaction, water has to be the base. Okay? And so as we will see, water can act as an acid and a base. It's very unique in that way. Okay? So now when this reaction goes, the acid donates a proton to the base accepts the proton, and what we are left with is this thing called the hydronium ion, H3O plus. It looks like this. It's an oxygen surrounded by 3 hydrogens, and it has a positive charge, okay? And then, of course, we're left with a chloride because the HCl bond broke up and gave us a chloride, okay? There's another shorthand way that we can write this reaction, and I'll show you what that is. I can write Cl gas, and I'm going to put the H2O liquid over the arrow. So this is kind of showing you so HCl exists as a gas in the absence of water, and we could bubble that gas into a container of water, okay? And so that's kind of what this is showing you without necessarily showing you the reaction to H2O. So we can say HCl gas dissolves in water, and that makes H plus aqueous plus Cl minus aqueous, okay? And in chemistry, this H plus, I'm going to put like a kind of equals sign. We often say that the H plus is synonymous with the H3O plus because technically, so let's say, technically, this is more correct. That's what's really going on in an acid, okay? It's not just a bunch of free protons floating around, okay? Because when water is present, water will absorb those protons because water is a proton acceptor. It's a base, okay? But when we write chemical reactions, generally it's okay to say H plus is the same as H3O plus. So this reaction is a shorthand way of writing this reaction, okay? So we can make these kind of shorter, more abbreviated versions of our chemical reactions, and we have to recognize that it does imply the same thing that this reaction is doing, okay? So keep both of those in mind. This is technically the full, complete reaction for an acid-base reaction, all right? But this one down here is also acceptable, okay? So just be familiar with both of those. Okay, moving right along. So now if we look at HCl, okay, still our acid, but now reacting with sodium hydroxide. Sodium hydroxide is a base, it's a proton acceptor, but as we will see, HCl, I've told you already, this is a strong acid. As it turns out, NaOH is a strong base. Water is not a strong base, okay, but NaOH is. And what makes NaOH a strong base is given by this picture right here, that when dissolved, sodium hydroxide will completely ionize into sodium plus and hydroxide, OH minus, okay? So now if we react this acid and base, check out what's going to happen, okay? We can see that there's an Na and a Cl, and they combine to make Na and Cl, right? This NaCl aqueous, okay? So what's happening to this H plus? Where is it going? Well, as it turns out, it's the hydroxide that's the base, okay? That's really what has the basic or even alkaline properties. So this hydroxide is absorbing this proton, and look at what the outcome is. H2O, right? When we have this OH, okay, minus, and this H plus, right? They're like little peas in a pod, okay? They combine to make H2O, okay? And so now what's also important to note, all right, sodium chloride is also a strong electrolyte. I'll just write strong electrolyte. So that means sodium chloride also is completely ionized. So what it means when I'm writing out this full reaction, and I've broken it apart in the ions, okay? Look, I've got chloride on the left side of this reaction, and I've got chloride on the right side of this reaction. So just like in a mathematical equation, when the left side equals the right side, they cancel out. And look, I've got sodium plus on the left side of the reaction and sodium plus on the right side of the reaction. So another acceptable shorthand way of writing this reaction, which is the reaction of any strong acid with any strong base. So let's say any strong acid plus any strong base always yields the following shorthand. I'm going to give it another name soon. I don't want to confuse you too much yet. For now, let's just think of this as a shorthand reaction, abbreviation or something like that. We actually call it the net ionic equation. I'm going to introduce that shortly. Okay? But any strong acid with any strong base can be abbreviated by writing H plus OH minus to make H2O liquid, and keep track of your phases. H plus is aqueous because it's charged. Hydroxide is aqueous because it's charged. And water is always a liquid unless it's a solid or a gas. So water can't be aqueous, okay? It's a pure material, all right? So that means water has to be a liquid, solid, or a gas. So you're going to hear me say that all the time. Water is always a liquid unless it's a solid or a gas, okay? So it's not aqueous. All right, moving